Okay. We're talking about nothing because you can't see it on the board. Okay, here we go. Let's try this. Gas laws. Now we're talking about Dalton's law of partial pressures. Remember all the gas law equations. See if you, pay close attention so you can follow me on this one. Okay, I don't want you getting lost. Dalton's law of partial pressure states that the total pressure exerted by a gas mixture is the sum of the partial pressures exerted by each component of the mixture. In other words, if I have a container with a bunch of gases, the total pressure is equal to the sum of the partial pressures of all the gases in there. I was kidding when I said pay close attention because all you have to do this one is be able to add and subtract. So for example, if I had a container that had oxygen with a partial pressure of 1 atmosphere, hydrogen with a partial pressure of 2 atmospheres, nitrogen with a partial pressure of 3 atmospheres, what's the total pressure of the container? 6. Wow, okay, there we go. And if we do the advanced part of it, I will give you the total pressure and all the partial pressures except one. So instead of doing addition, you have to do subtraction. Okay. And we all saw how well you did on counting. So, okay. All right. So here we have a 1 liter vessel contains 0.215 moles of nitrogen gas and 0.0018 moles of hydrogen gas at 25.5 degrees C. Determine the partial pressure of each component and the total pressure in the vessel. Yeah, that doesn't have this equation in it. But we can use PV equals nRT to find the pressure. So we know what N is, we know what R is, we know what T is, and we know what V is for each of the gases. So for the nitrogen, it was 0.215 moles. You do the math and you get 5.27 atmospheres. For the hydrogen, it's 0.0188 moles. You get 0.289 atmospheres. The total pressure, you add them together, 5.56 atmospheres. Okay? So, questions on that? Once again, the problem, I know you all wanted to see a direct problem, right, like I did on the board before, but life very seldom is direct like that. You have to do something else to get to where you want to go. Mole fractions, since it's a fraction, it's always going to be less than 1. So the mole fraction is the mole of the gas over the total moles of the mixture. And if you add up all the mole fractions of a mixture, it's got to add up to 1. And it's dimensionless. You can also figure out mole fractions by looking at the ratios of the pressures. So you can take the pressure, P sub I, of an individual gas and divide it by the pressure, total pressure of the mixture to get the mole fraction. So the mole fraction times the total number of moles, it's just rearranging the equation, gives you the number of moles of that component. Similarly, if you have the pressure of the mixture, you multiply it by the mole fraction of that component, you get the partial pressure of that component. Where do you think it might be important that you know the mole fractions or of gas mixture? What?
Interaction.
Well, yeah, interaction, but give me something more specific. Yes. So, let's see if you're going to go maybe deep sea diving or scuba diving and you got one of those breathing tanks on. Those are a mixture of gases. So you want to make sure you got the right mixture before you jump down to the bottom of wherever you're jumping down into. So calculate the mole fraction of NO in a 10-liter gas cylinder at room temperature that contains 6.022 moles of nitrogen, in which the total pressure is 14.75 atmosphere. And what do we say? Did we give this a temperature? Yeah, 25 degrees C. So remember, you have to, your gas laws, you have to take the temperature in Kelvin. Total moles is equal to PVRT. So we know the total pressure was 14.75 atmospheres. The volume was 10 liters. RT, we know the total number of moles is 6.029. We know the moles of hot nitrogen was 6.022. So we subtract that from the total moles to get the moles of NO, 0.007. So the mole fraction of NO is 0.007 divided by 6.029 is 0.001. I was just thinking another place you might want to know the mole fraction, make sure you got the right mixture, just in an operating room if you're giving someone anesthetic. You want to know what the mixture is, so that you want them to go to sleep, but you don't want them to go to sleep permanently. And you certainly don't want them waking up in the middle of the surgery. Although I have heard that it does happen. People complain that they wake up, and of course sometimes they'll give you a paralyzing drug, because they don't want, you to get the tube down your throat and that, so they're awake, they can't move, and they feel the operation. I assume it's not pleasant. So here's an example of setting up partial pressures to solve problems. Here we have potassium chloride, a solid. If you heat it, you get potassium chloride plus oxygen. So here they have potassium chlorate and magnesium dioxide, or manganese oxide rather, manganese 4 oxide, and you're heating it, and you're calculating the oxygen by displacing water in the cylinder. And you get the partial pressures of water at certain temperatures. So that's how you could set up a reaction like that. Potassium chloride, by the way, is very, I always wanted you to do this. You take that freaking tube like you had and you heat it up with a gummy bear. Apparently, like the gummy bear catches on fire or explodes. Yeah, I don't want to do it with a big gummy bear. Okay. So what happened? I put the sodium in the ice. Yeah, well. Here we have calcium metal reacts with water to produce hydrogen gas and calcium hydroxide. Determine the mass of hydrogen produced at 25 degrees C and 0.967 atmospheres when 525 milliliters of the gas is collected over water. So the volume of the gas is 0.525, temperature 298.15. Using that table, the partial pressures of water, 25 degrees C is 23.8 torr, or converting it to atmosphere, 0.0313 atmosphere. And the molar mass of hydrogen is 2.016 grams per mole. So what do we do with that information? Well, the pressure of the hydrogen is the pressure, total pressure, which is 0.967 atmosphere minus the pressure of the water, 0.0313. So the partial pressure of hydrogen is 0.936 atmosphere. The moles of hydrogen is equal to, so here we're rearranging the ideal gas law, so we end up with N is equal to PV divided by RT. So 0.9357 atmospheres, which should be 0.936, times 0.525 liters, which was the volume, divided by R and T. We had 2.01 times 10 to the minus 2 moles. And moles converted to grams, we end up with 0.0405 grams of hydrogen. So if you're producing a gas, you can calculate how much gas is going to be produced. Which may be interesting, you know, at least from the safety factor, you want to know how the pressure might build up in a reaction. So if you were to take baking soda and vinegar, you know, you leave CO2. So if you put that in a soda bottle and cap it, by knowing how much you put in there, you can calculate how much gas is going to be produced. And from the volume and the temperature, you can calculate the pressure. And if you know what breaking force is in the bottle, you can calculate how much you need to put in there to blow up the bottle. Just saying. Well, let's look at the kinetic molecular theory. How it gives rise to the macroscopic, or everyday properties of gases. So, kinetic molecular theory is a gas is composed of particles that are separated by relatively large distances. So the gas is mostly empty space. So if it's mostly empty space, you can push the molecules together. Nothing to block you. So gases are compressible. I.e., we have in this room, fire extinguishers. So that's compressed CO2. And you can shake one of those, it's actually compressed, so it's a liquid. When you release the handle, it comes out as gas. And when it expands, it cools. So that white stuff, when they cloud, is actually water vapor condensing. As opposed to a liquid. In a liquid, you can't compress. These molecules are too close together, which is why hydraulic brakes work. That's why a car stops. Again, if you do a brake job, you have to bleed the brakes to get the air out, because we said air is compressible. If you don't, you go to stop your car, your brake pedal goes to the floor, and eventually the floor comes up to meet you when you hit something. So gas molecules are constantly in random motion, moving in straight paths, colliding with the walls of the container and with one another in perfectly elastic conditions. So we don't lose any energy. It's transferred. So gas molecules do not exert attractive or repulsive forces on each other. That's the kinetic molecular theory. So pressure is the gas molecules hitting the wall. So if I have a container with a certain number of molecules in there, A, They're moving with a certain speed. If I heat that mixture, the molecules are going to move. So now instead of this, it's, and what did I say the molecules hitting the wall cause? Pressure. So if I'm doing this faster, the pressure is going up. So the pressure is going up. And you say, well, duh, yeah, if I take an aerosol can and throw it into an open fire, it's going to explode. Explodes. The average kinetic energy of gas molecules in the sample is proportional to the absolute temperature. So the energy is 1/2 mass times the velocity squared. So the bottom shows you how to calculate the mean square speed. So remember, we got molecules in this gas mixture moving around with various speeds. Some are moving faster than others. But we calculate the mean square speed. So like I said, we can tell you the gas are compressible because there's a large distances between them. And pressure is gas molecules colliding with the walls. So it's the frequency of collision and the speed of the molecules when they collide with the walls. So if I decrease the volume, I increase the frequency of the collision. Does that make sense? Or not, if you don't understand. So if you were all gas molecules, and I said, okay, go and hit this side of the wall, then run across and hit this side of the wall, then run across and hit this side of the wall, there's going to be a certain frequency you're hitting. You got to run back and forth. If I decrease the volume by moving the walls closer together, you can get from one side to the other a lot faster. So there'll be more collisions. If there's more collisions, there's more pressure. Okay. Huh? So again, starting with the walls again, you're running back and forth. And if I just start to say this room is going to run back and forth, this side of the room is going to run back and forth. There's 4 of you here. So you're going to run back and forth, you're going to hit with a certain number of collisions. So now if I say, okay, we're going to add these people, so you're all moving at the same speed, there's going to be more or less collisions. Yeah, and there's going to be more collisions, more people. So if I add gas to a container, the pressure is going to go up. Just like a balloon, you keep adding more and more to get to the point. So, all right. Now I get everybody running back and forth, and you're hitting it with a certain frequency. Now some people come in with blowtorches and try to hit you in the butt with them, and you're going to run a little bit faster. So as your temperature increases, you're going to hit it faster, so the pressure is going to go up. Why do we make it so hard? I don't know. So heating the sample increases its average kinetic energy, which is the energy of kinetic energy is the energy of motion. Thank you. You want to throw this. Dalton's law of partial pressures, because we're assuming that gas molecules don't interact with each other. So Nat's back there running back and forth, bouncing off the walls. And Hillary's up here bouncing up and off the walls. So to figure out the total pressure in the room, I have to add this collision to your collision. That gives me total pressure. But individually, you're not interacting with each other. He's hitting the walls 10 times a minute, and you're hitting it 5 times a minute. The total is going to be 15, but he's 10 and you're 5. So you're not interacting with each other. Conversely, if I know it's 15 and I look at yours is 10, I know his has to be 5. So that's just looking at the molecular speed and the root mean square. I'm not going through all the math. is 3 RT over M. But basically, what it says, if you look at this graph, the number of molecules and the molecular speed, as the temperature goes up, you can see the average is increasing. Molecular speed is increasing from left to right. So 700 K, we have more molecules down here than at 100 K. So the higher the temperature, the faster the molecules, on average. So the greater the pressure in a sealed container. So here we have just one temperature, 300 K. We have chlorine, nitrogen, and helium. Why the difference? Why are there more molecules of hydrogen at a higher speed than of chlorine at the same temperature? Yeah, chlorine is what compared to hydrogen? Denser or heavier, right? So again, you know, you've got some little lightweight running back and forth, and I'm trying to run back and forth. It takes a lot more energy to get me moving. Well, I'm going to be moving a lot slower than they are. So what I can do is say that the root mean square speeds or velocities are equal to the square root of the proportions of the molar masses. Square root of the molar masses. So here's the problem. Determine how much faster a helium atom moves on average than a CO2 molecule at the same temperature. Helium molar mass is 4 grams per mole. Carbon dioxide is 44. Use that previous equation. So when you do it, you got to flip the molar masses. So you get the square root of 44 over the square root of 4, 3.316. So a helium atom moves 3.316 times faster than CO2. So if I have two containers, one filled with helium, one filled with CO2, I'm going to heat them, assuming the containers are identical. Which one's going to burst first? What? One's got helium, one's got CO2. Containers are identical. I'm just heating them. Which one's going to burst first? Why? It moves faster. Helium moves faster, so I heat it, it's going to be even moving faster. So, I'm assuming the same quantity, molar quantities. It's going to increase the pressure faster. Diffusion and effusion. Diffusion is the mixing of gases as a result of random motion and frequent collisions. So there we have the pink gas on the left, the yellow gas on the right. You open up the stopcock in the middle, eventually they both mix. So if someone comes in wearing some strong perfume or cologne and sits at the back of the room, eventually I will smell it, because it'll diffuse through the air. And it won't stop. It'll go out into the hallway or whatever. It'll be to a point where I can't smell it. Sure. A bloodhound can. Diffusion is the escape of gas molecules from a container to a region of vacuum. So it had good old Graham's law states that the rate of diffusion or infusion of a gas is inversely proportional to the square root of its molar mass. Huh? So as the molar mass increases, is the rate of effusion or diffusion going to go up or down? What? I didn't hear what you said. So as the molar mass increases, is the rate of diffusion going to increase or decrease? Yeah, as m gets larger, 1 over n, or even 1 over the square root of it, is going to get smaller. And what did we say before about it? Remember we had chlorine, I forgot the other one was nitrogen and helium. Remember at a given temperature, the helium moved a lot faster because it was lighter. So a heavier gas diffuses slower than a lighter gas. Well, everything we talked about was about ideal gases. It turns out there's no such thing as an ideal gas, but that's how we use it for our equations. What causes it to deviate? At high pressures, gas molecules are close together. So remember, kinetic molecular theory assumed the gas molecules are far apart. But at high pressure, they're not. They're closer together. So we can't assume that the gas molecules occupy no volume. So as they get closer together, the volume occupied by each individual molecule becomes more significant. You know, if you guys are spread out all over Smithfield, no one could really, oh, okay, here's a person, here's a person, here's a person. There's no significance to how far away. But as you come closer and closer and closer, now you're all in this room and go, oh, this is my class. Your presence is more significant. See, you are significant. So at low temperatures, gas molecules are moving more slowly. So we said before there weren't any interactions between gas molecules because A, you were far apart. Think of you all spread over Smithfield. B, you're moving rapidly, so you're all in your cars going 70 miles an hour. You don't have time to interact with each other. So now we bring you close together. Take with your cars. Now you're in this room, now you can interact with each other. So you have lower kinetic energy, obviously, some of you aren't moving. So your interaction forces become more significant. So there's an equation, I'm just going to run through it, you don't really need to know it. The pressure of an ideal gas is equal to the pressure of the real gas plus AN squared over V. V real is V ideal minus NV, and we'll go into what those mean. So there's a corrected volume term, there's a corrected pressure term. So there's some values for A and B for different gases. So you'd actually put those terms in, and we're not going to do any of that in any of the tests or anything. So just to show you that if you really want to do it in real life, you have to correct for how things work in real life. I'm going to kind of skip that. So one way is you can talk about how you measure how far a gas is going to deviate from ideal behavior is by its compressibility factor Z. Z is equal to PV over RT. So for 1 mole of an ideal gas, Z is equal to 1 at all pressures and temperatures. So here we look at ideal gas. There's a straight line. But there's nitrogen, methane, hydrogen, and ammonia. You see, as you increase the pressure, well, for methane and ammonia, the compressibility actually goes down initially, but after a certain pressure, it goes up and becomes more and more compressible. Compressibility factor. So, okay, look at this one. As the temperature goes up from 200 K to 1,000 K, the compressibility factor goes down. Why? Yeah, they're moving faster, so they're hitting the walls harder and harder and harder and faster and faster and faster. It's harder to compress it. It gets heat. Well, the pressure builds up. So it's harder to compress it. You're pushing back against that pressure. And that is all she wrote.